All right, you're welcome back again. I want to look at SVM, meaning support vector machine. It's one of the most powerful classification model or algorithm when it comes to uh, classifying binary data. I think support vector machine seems to be the best as far as I'm concerned, based on experience. It's very powerful too when it comes to binary classification. And it also helps to separate to find the optimum hyperplane that best separate the classes into feature space. And if you check our slide last time, I described how it works here. That it used the uh, maximum margin, okay, to separate the factors. Those four factors are the one at the edge of the margin, okay. So at the edge of the hyperplane, positive hyperplane, negative hyperplane. So yes, this line in between here is called the optimal hyperplane. So this is the most optimal that it could find. Until you find the optimal hyperplane to separate it, then it stops. So that is support vector machine. So it's a very powerful tool when it comes to classification of data. I want to demonstrate this using uh, R. So let's load our data set. Let's load library first. We are going to load caret, and this particular E1071 is the library for SVM. Okay, this is for SVM, and this to perform classification and regression analysis. So let's load our data set. We are still using the same data set to see how we can use different algorithm or different models to classify them. So let's we have seen it before. We glimpse it, then we also omit the data. We summarize again to see if the NA or missing data has been cleared off. All right, so let's set a seed and split the data into 70 to 30%. And we go ahead, let's run this together. So we have done this several times. So they follow the same principles in machine learning. They are the same concept. So we just need to separate this sample into two sets, training set and testing set. So we have 70%, right? 70% and 30% of training 70%, test 30%. So that's what we are doing here. So we run this line. All right, so we want to use in this now, SVM is a very powerful tool. Like I said before, you can use what we call 10-fold cross-validation here. So we create a control from a control function from SVM. The method is repeated cross-validation. So we pass a number 10 iteration, repeat 3 times. All right, so we create a cost. In this cost now, we have to create our C. It's one of the SPM parameter tuning system. So one of them is cost. So we have a few of them as well, right? But one of the major one is cost. So we want to see then this cost 0.1, 0, between this sequence 0. From 0.1, then to 0.5, all right, 0.5. So we want to see in this sequence which course at the fall in between this range that can get our margin, maximum margin. All right. So that is what you're trying to see here. So we are now create a new object here called SVM model. Can give it any name. So we train here. Our diabetes is still our target variable. Then we pass all the remaining data inside. Okay. Now our train data is this, which we created here. Don't forget. Okay, our train data. We want to train first, but we now test. Then our method is SVM linear. This method we are using. So there are many modern methods. We can use SVM radial, polynomial, and the rest. So it's more than one. So if the one is not okay, you can change to maybe radial and see the result may be better. All right, so we are using SVM linear. So if SVM radial, just change to R radial here. Just see SVM radial. Okay, so that's what it means. So we have a preprocess center in inbuilt scaling. of SVF. So we are asked to scale to do the inbit scaling for us. So we call our control we have created here. Our control, we create a control here. We pass it here. This control we created here before for cross validation. We pass into this. So our tuning here is grid. We try to use to tune using our cost. C is cost. We pass it here also. Okay. So these are the things that we created for the model. So this is a very powerful model, and I hope it will work better than the rest. So let's run where do we stop before? So let's run this control main cross validation first, and go ahead and run the grid. So let's run the model itself now. All right, so we run it's still running now. It's start to I'm not trying to show the process. So it has finished. So it has finished running. Then let's see the model. What that look like. Let's see the model summary. So we are just run this. So in this model, it's trying to tell us support virtual machine. This is called linear kernel. What we use now. We have radial kernel, we have polynomial, and the rest. So in this linear kernel, we have 273 samples. Sample is small. The support virtual machine have no problem with small samples. They can handle it perfectly well. Then we have 8 predictors. That's our what they call it, our clinical variables. All right. So we have 2 classes, negative and positive. All right. The preprocessing center and scale all the 8. Okay. The sampling cross validation 10-fold repeated 3 times. All right. Some summary of sample, which is the summary of samples we have. Then resampling is also accompanied by 20 parameters. So the parameter 20 now, what we are looking at now, we have accuracy, we have kappa, this is cost. So from this cost, which one give highest? So it's trying to look at help us to find which one give highest from this cost. Okay, 73, 74, we have 74, 74.03. So it's anyone, I think it should be around here. You can pick anyone around here, around this place. So I think it can be 3 point something. So you can pick C74, seems to be highest for training. All right, it's for training. So it is okay. Pick 3.01, 3.01, 3.01 gives 74. Okay, and it gives also the highest kappa here also, one of the highest kappa here. So that is what support factor. So we say the accuracy was used to select the optimal model using the highest value. The final value used for the model was C. So this is just a for the training process. So let's test the data on the training test. Let's just run it on testing. So if you run this multifunction matrix now, you should be able to test our model. So let's see what we get. We get 84%. 84%. Okay, so that is good enough. Okay, so that means there is a more that we have not been able to see under that. So 84% 84% accuracy is good. So let's see how we can plot this scatter plot and to separate hyperplane. So to say that, let's first initialize our data to 0.05. You can change this as you want to give more space to the hyperplane. All right, so let's run this line of code and then run. So our test data we are using now to plot the graph. Our factor variable is called the diabetes. That is our target variable now. So we are saying if else test variable we are plotting against glucose against insulin. All right. So you can just change here the one that gives you best hyperplane can change. So you can also check also using maybe psych library using a ps.panel to see which one that is more correlated among each other. All right, so we create a p plots here. We call it just a variable called p, so we can just change it. So p, we want to use ggplot. Our data is test data. All right, we pass it in. Our aesthetic is S glucose, Y insulin. All right, we are trying to see our color is diabetes. All right, that is separated by diabetes. So we are trying to see how we can separate the positive from negative. So the point we have size 3. You can increase the size if you want the bigger points. So now we want to pass additional boundary lines now. That P we call the P here plus P, new P now, we create a new P plus P geo line. We want to create a straight line to divide the line. So we have a dashed line. So we create this. So that's how data we pass in the data, and we run the analysis. So if we run this analysis now, let's say we run this line downward, should be able to give us a. All right, so this is what we have. That's what we have here. That's what we have. So it was trying to help us to create an hyperplane here to divide this. So these are support. Those ones that touching the line are called the support factors. So these are the opposite, and so this diabetes 0 and 1. So these are the positive and negative. So look at this. So you can do better. You can improve on this plot and make it do better. All right. So this is what we have. So you can just see the plot here. Okay. Let me see. I can break it. Let me try and see. I can break it down so that it can be visible, properly visible. We have this. Okay. What do we have here again? We have this. What do we have again? We have this. I'm going to break it down so that it can be visible. We have this. We have this. Okay, so I think this is visible enough now to see. All right. So anyone can see this now. So that is so you can zoom this out to see how big it is. So it divided the red up the other color here down here, so to show that this is called hyperplane. So there are many ways to do this actually. Some code are more complex, but at least this is simple. Just simple to show you example on how to divide the hyperplane. So you can improve on the code and make it better. All right. So this is just to show how to learn using SVM, and with as much as data you have, then you can now plot the hyperplane. So I will see you in the next class where we look to another learning algorithm. So thank you so much. I'll see you later.